Section 2.6 is on special functions. Special function we're going to look at first is called a piecewise function, and that is a function that has two or more parts to it. So to examine this, we're going to take a look at an example. Here it says graph the function and state the domain and range. So the piecewise function reads f of x equals negative 3x if x is less than or equal to negative 4, f of x equals x if x is between 0 and 3, including 3, and f of x equals 8 if x is greater than 3. Remember that f of x is just a special way to say y. So what this really means is that y equals negative 3x when x is less than or equal to negative 4. And look at it here on a number line. So when x is less than or equal to negative 4, we're going to graph the function y equals negative 3x. Y is equal to x when x is between 0 and 3, including 3. So on this interval right here between 0 and 3, not including 0, but it is including 3, y equals x. And y equals 8 when x is greater than 3. And that's this interval here, wherever x is greater than 3, y is going to equal 8. So the trick to graphing this is we're going to graph each line separately, do it lightly and with pencil, and then erase the part of the graph that doesn't apply. So let's try this. Okay, so remember this just means y equals each one of these parts. So let's start by taking a look at what y equals negative 3x looks like. So our y-intercept is 0, and that means I go down 3 and right 1, and down 3 and right 1, or up 3 and left 1. And if I were to connect the dots here, that would be the line y equals negative 3x. But I only need the part of this line where x is less than or equal to negative 4. And right here, x is negative 4. So I only need the part of this line that basically starts here, and unfortunately I don't have enough graph, but I think I'll go ahead up, and so if I go up 1 and then 2 more and then 1 over here, so my next point would be something about there. So that's the only part of the graph I need where x is less than or equal to negative 4. So it's actually just going to look like this. Oh, let's see, that's not quite straight enough. So it's going to look something like that, because that's where x is negative 4 and y is 12. So I really don't need any of these dots here. I just use those to help me figure out what the line looks like. The next part of the graph says y equals x between 0 and 3, including 3. So the line y equals x is this line right here. So whatever x is, y is the same number. So that's a perfectly diagonal line with a positive slope of 1. Now I only need the part of that line from 0 to 3. So I don't need any of these points down here. And actually here at 0, this needs to be an open circle. And right here, x is 1, x is 2, x is 3. So that's the only part of that line that I need. I just need the line y equals x only on that interval. And then the fourth part, the third part, y equals 8 if x is greater than 3. And remember, the line y equals 8 is a perfectly horizontal line through 8 on the y-axis. And I only need the part of that where x is greater than 3. So right here, x is 3. And so I'll have an open circle there since it's a greater than. And it goes like this. And that's a piecewise function because it has 3 different pieces to it. So let's take a look at what the domain is. Remember, the domain is what can x be. So my domain is the set of all x such that x, now can x be anything? No, it actually can't, because a good way to look at this is to look back at the number line that we drew here. So x can be less than or equal to negative 4, or, looking at the graph here, at the number line here, anything greater than 0, or x is greater than 0. And our range is going to be any of the y values, whatever y can be. And We can use y or f of x, it doesn't matter. I'll go ahead and use y. The set of all y such that y is, so what can y be? Y can be anything greater than 12, because that's this part of the graph right here, greater than or equal to 12, or y is equal to, now my y's right here go from 0 to 3, so actually I think I'll write it like this. 0 is less than x, which is, I'm sorry, less than y, which is less than or equal to 3, and that's the y's on this part of the graph here, or y is equal to 8. So those are all the values that y can be in this graph. So piecewise functions are a little bit tricky, but they're actually kind of fun if you break it down into different parts. A special type of piecewise function is called a step function. And one type of step function is called the greatest integer function. And it's written like this: f of x equals, and you'll notice the x is in a double set of square brackets. And that means the greatest integer less than or equal to x. So for example, if we did the greatest integer function on 7.6, the greatest integer less than or equal to that number would be 7. If we did the greatest integer function on negative 8.3, that would produce negative 9. Basically, you round it down to an integer. And if you're not sure you can do this on your calculator, go to the Math menu, select Number, and I believe on my calculator it's number 5, go down to Integer, input the number, hit Enter, and it'll give you the greatest integer. And here's an example of one that I found in a textbook. So you can see obviously why it's called a step function. It looks like a bunch of steps. And you'll notice that for a whole range of x's, so for several x values, the y value stays the same. So this right here is where x is between negative 3 and negative 2. X can equal negative 3, but it cannot equal negative 2. And all along that line, the y value is negative 3, as I said in the chart here. Then it takes a jump up to y equals negative 2, and for all x values between negative 2 and negative 1, including negative 2 but not negative 1, the y value is negative 2, and so on. One thing that I find interesting is that if you were to connect all of these dots right here, that would be the function y equals x, or the basic diagonal line through the origin. And then it all goes off to the right a little bit with an open circle. And the last type of piecewise function we're going to take a look at is the absolute value function. And you may remember this from Algebra 1. It's a piecewise function that ends up looking like a V. So here we're going to graph the function and state the domain and range. So we have f of x equals the absolute value of x minus 3. Now remember, since this looks like a V, this point down here, we're going to call that the vertex. And I would like to find what that value is so that I can choose some values to the left and some values to the right, so that when I graph it, it does indeed look like a V. So to find the vertex, we're going to take the stuff that's between the absolute value bars and set it equal to 0. So x minus 3 equals 0, and adding 3 to each side, x equals 3. That's going to be the value of my vertex. Oops. I am going to put that in the middle of my table right here. And I'm going to choose 2 values smaller and 2 values greater than that. And then go ahead and plug those in. So when I plug in 1, 1 minus 3 is negative 2. The absolute value of that is a positive 2. When I plug in 2, that gives me a negative 1. The absolute value of that is 1. When I plug in 3, I get 0. I plug in 4, I get 1, and 5, I get 2. So let's go ahead and graph that. Maybe I'll do it here in pink. So I'm going to have the point 3, 0, 4, 1, 5, 2, 2, 1, and 1, 2. And there is your absolute value function. And you'll notice it looks like a V. And as we'll find out in the next section, there's actually a really good reason, or we can explain why it is shifted to the right. Now the domain is going to be all real numbers, the set of all x, such that x is a real number. And my range is going to be the set of all y such that y is, and let's take a look at the graph. So what values can y be? Doesn't look like y can be anything negative, so y has to be greater than or equal to 0. So in this video we took a look at some special functions, and in particular piecewise functions, both those that look kind of funky with several different parts to it, a step function, as well as an absolute value function.